right, let's talk about how we can use an initialization list to initialize arrays, and then we'll talk a little bit about arrays in memory in this segment. All right. So as we saw before, if we just declare an array with a size and don't store anything in it immediately, it has garbage values in it. But we can use what's called an initialization list following the declaration. So remember, when we declare any sort of variable, it has to have a data type, it has to have a name. In the case of an array, then we use the bracket notation and specify the size. We use the assignment operator, and then inside curly brackets, we have this initialization list, so a list of values. Right? They're constant expressions. They're separated by commas when we have more than one. So in this example here, right, if we declare an array named A, its data type int, its size is 5. Inside the curly brackets, we have 77, 19, minus 13, 5, 81. It's going to have a one-to-one correspondence. The first thing in the list here will get stored. So index 0 will get stored with the 77. Index 1 will get the 19. Index 2 will get the minus 13, and so on. So let's just go ahead and actually show that in code. Right? So here's a coding example where I've just declared the same array named A. It's of type int. I went ahead and built it. Here's our initialization list. And if we just take a look at what's in memory here, we can see A at index 0 has the value of 77. We have a value of 19, value of minus 13, and so on. Right? So notice then I have 5 elements in the list here. If we don't have 5 elements in the list, right, if we have less than that, we'll see that it will initialize the rest of those array elements to 0. So what if I just have 2 items in the list here, 77 and 19? We stop the debugger. I'm going to put my cursor here, right click, run the cursor. Right, it's going to rebuild. It's going to rerun that declaration and this initialization up above. And so now you can take a look in memory and you can see, well, index 0 has the 77, index 1 has the 1 or the 19, and the rest of the items are initialized to 0. So when your list is shorter, your list of elements, then it initializes the rest to 0. Right? That's what the next lecture slide gives you an example of. What's handy about the initialization list, right, is if we want to initialize everything to 0. That's what we commonly use. Because if you think about it, if we had an array of 100, we don't want to be typing in 100 array elements. I'm not quite sure why I changed the size to 6 in this from 5, but let's go with that. All right, so here's an array named A, type int, 6 elements. So it's size 6, and we're going to initialize all of those to 0. And let's just go back and do that in code. Let's just stick with a 5 here. All right, so we can see then if we just put the 0 in here, and you only need a single 0. And what this does is when we just have one item in the list, so let's go back to when we had 2 items in the list. Remember, we only had 2 items, but our size was 5. It just went ahead and initialized the rest to 0. Technically, what happens if this first 0 is here, it says, okay, I'm going to initialize the first element to 0, and then because there's nothing else in the list, it initializes the rest to 0. And this comes in very handy for us. So we stop the debugger from that previous turn, right click, run the cursor, right, which is a control F10. I could use that shortcut. And now if we look at our array in memory, we can see that every element has zeros in there. Right, so that is very, very handy, right? Especially sometimes we use arrays to hold sums or counts. So if we were trying to maintain a count of something and had an array where we wanted to set everything to 0, that would be very handy. And this will work even if I make this 152, right? If I make this different sizes, again, run the cursor. This creates an array of 152 elements. It initializes everything to 0 for me. Right? All right. So that is extremely handy at times. And that's what we most often use it for. Let me show you this would work if these were doubles. And let's go back to a more reasonable size. It's easier for us to see on the screen. I'll just actually pick 3. Let me use a double type constant there. So I match my data type. Right. Run the cursor, so we rebuild. And you can see now in memory, right, I have an array of doubles of size 3. Each individual element is of type double, right, and they're all initialized to 0. And can I use an initializer list? What doubles can I say? Oh, well, let me make this 1.0, maybe make 2.2, maybe I'll make this one 3.3. Yes, that needs to be a comma, not an extra decimal point. So, all right, remember the initializer list needs to just be a constant expression. Just I'm going to rebuild, rerun. All right, so now our array of 3 doubles has the value of 1, gets assigned index 0. This gets assigned index location 1, right, the next one, third one on the list, third array element. Right, notice then it can't represent 3.3 perfectly, so it's rounded it to 3.29999, right? We know that about floating point. Some numbers it cannot represent perfectly in floating point. Once again, works for ints, works for doubles, right? I can do this with chars, right? Maybe I call it alphabet. Now I'm going to be too lazy to initialize them all. So if I just say, let's make the first one A, the second one B, the third one C. You don't need the spaces in between. I'm doing that to make it a little more readable. Fourth one D. Do my run to cursor here. So we rebuild. Okay, you can see the array has A, B, C, D in it. Right. So this shows you the character value. It also shows you the integer value for the ASCII representation. And then notice, like we said, if we don't have, in this case, we only have 4 elements. Our size was 26. So if we don't initialize everything, the rest of our list gets initialized to zeros, right? And the character interpretation of a 0 is a \0, right? Which is why this is showing up. You can see the number 0 is initialized there. So any data type we want, we can create an array of that data type. We can use an initializer list with that. All right, like I said, comes in most handy whenever we want to initialize things to zeros. One other thing that you sometimes see is you see this notation that the program, the compiler decides on the size of the array based on an initializer list, the length of that list. So look at this notation here. We've got a data type, we've got the name of our array, and we have empty brackets. Notice there's no size, but there is an initializer list that has how many elements? 1, 2, 3, 4, 5, 6. So it would create an array of size 6. So let's go ahead and see that happening in code as well. And actually, in this case, let's just stick with the char, right? So here, we're going to keep our 4 elements in the list. Our data type, the name of my array is alphabet. I've got the empty notation here. Let's rebuild this. And now you can see it created a character array, a char of 4, right, and initializes those 4 elements. So it determined the size of this based on the list. This is not something you will commonly see. I think they threw it into the textbook, right? I wanted to throw it out there, but it is used sometimes more or less for constants. Something we might see later in the course. For now, we won't talk about that because I can't show you the ways that we might use it. But I will show you how to use some of these later in the course. So I just wanted to show you that, right? It's in the lecture notes, it's in the book. It's not something we're going to commonly see. We're always going to specify our size for the most part in our homework. Right. So the last thing then I'd like to talk about is arrays in memory. We've not talked about much about memory models. So this is a memory layout. It says if a C program, it's the same for C++, right? So in memory, right, if you've heard of RAM, random access memory, when our programs start running, right, our programs are placed into memory, right? As things are running on the CPU, the central processing unit, right? Out in memory, there are different segments of memory. Right? So this is showing you, and everything is tracked by addresses. So everything in memory has a unique address. So this is saying that your higher addresses are up here, your lower addresses are down here. So there's a text data segment, right? Your program might be put in your text data segment. There's a segment of memory where initialized data is stored. There's a set where uninitialized is stored. A lot of this relates a little more to things that are declared globally. And what we're really concerned about, what we're going to be concerned about over the coming weeks, is our code, when it runs, the variables we declare in our programs get placed on the stack. And later we'll learn how to dynamically create memory. So everything we're doing is, our memory is allocated or is known ahead of time because it's statically created. Everything's put on the stack. Later, when we learn, after we learn pointers, we'll learn dynamic memory allocation and where things go on the heap. But for now, we're just going to realize that our information gets stored on the stack. We also haven't worked with command line arguments either. So our information is going to get stored out here in the stack. The stack data structure, we will take a look at some data structures later, is what's called a last in, first out. So LIFO is a last in, first out. Meaning when you work with a stack, we push things onto a stack. So think of a stack of plates or a stack of books, right? When you put down, say, the first book, that's the first one in the stack. If you lay another one on top, so look, this container has sides, basically showing you can put something in here, right? Because it's got a barrier here, it can't come out here. The next thing we put in goes on top, the next thing gets stacked on here. That's called a push operation on a stack. So we push things onto a stack. When we want to remove things, we can only remove the topmost element. And when we remove things, that terminology is called a pop. We pop one element at a time off of a stack. Like I said, we will come back to data structures later, but it is a special data structure, right? So when we're working with memory, I might talk about pushing things into memory and popping things off of memory, right? So we're using this stack data container in the stack memory area. So that area is where automatic storage class variables are stored. So whenever we when we declare our variables, everything we've been using is an automatic storage class, right? Things that we declare locally within curly brackets and all, those are the automatic storage class variables. When we call a function, some information is stored as well. So every time we call a function, there's something called a stack frame that's created. Within that stack frame, it then stores function parameters, the function's return address, saved previous pointer. So we don't need to remember, we haven't talked about exception handler, so ignore that. But for our functions, we know that we work with parameters, they'll get stored in memory. Return address, so when we call a function, the program needs to know where to return when that function finishes running. And then any locally declared variables within our function will get stored out in this stack frame. Right. So we don't go into great detail, and that is no detail at all there. What's important then is we'll talk a little bit in the future when we get to pointers about memory addresses. So everything on a computer is stored in a byte. A byte of information is 8 bits, 8 binary digits. So all of our memory is comprised of bytes. These bytes all have addresses. So in this example, right, this particular case, the lower address number here is starting at, these are hexadecimal, right? At this number, and you can see it is getting larger by 1 byte, from 0 to 1 to 2. So each one of these little cells right here represents a byte of memory. All right. Now over here, this is showing you that if we have a variable named sum, it's of type int. This is saying that if an integer takes up 4 bytes, right, and the value of this variable sum happened to be, so it's going to show you then all 4 bytes, and then so 0, 0, 0, 0, 0, 0, FF, right, is what's stored in memory, or decimal value 255. This is how it's represented in binary. So for binary, for a byte, we usually show you 2 nibbles, 4 bits at a time, because this is hex, right? So this is hexadecimal notation. Remember, hex and 4 bits is equivalent to 1 hexadecimal digit, which is why you're then seeing for 32 bits, so 4 bytes, 8 bits in a byte, 32 bits. 32 bits, then we end up with the 8 hex digits here, right? My long-winded way of getting there is saying that this value, you can see this set of 00 is stored in this byte. This 00 is stored in this byte. The next 00 is stored in this byte. And the last, the FF, is stored in this byte. So this particular scheme is storing, this would be a higher order byte in the lower address. And then as the addresses increase, right, it's storing these bytes. So we need 4 bytes for this. So you can see here, age is of type short. Now a short is half an int. So a short takes up 2 bytes of memory. In this case, this is saying this particular short has a hexadecimal value of FFFF. So technically this first FF is stored here, the second FF is stored there, right? And this is just showing you how variables, as they're declared, basically are placed into memory. If we need 8 bytes, it's going to use then these 8 bytes, and they all have a specific address to refer to that particular byte location. So everything then is stored contiguously in memory. So as variables are declared, they're stored in the next stack memory space. They're actually pushed onto the stack. So in this case, this is saying that the stack would have a lower address and it would grow from low to high. Now sometimes a stack doesn't do that. Sometimes a stack will grow from high to low. Right? We won't worry about that right now. Right? Once again, the number of bytes required depends on the data type. So this is just to point out that information is stored contiguously in memory. And the same thing happens then with arrays. When we declare an array, in this case we have an array of type int. Right? It has 5, its size is 5, and it's initialized to then these 5 values. Well, theoretically, in this example, if our lower memory address location was address 1000 and the int required 4 bytes, we often would show that the int was stored here. Index location 0 refers to byte 1000. Index location 1 refers to byte 1004. It points to those addresses, but when we refer to that area of memory, because it knows it's an int and an int has 4 bytes, it will bring back all 4 bytes. That's going way beyond what we need to know. For now, just know that arrays are stored contiguously in memory. Right? When we talk about pointers, basically we'll learn that this index is an offset from this particular memory address, and it will know how many bytes to go to retrieve this. So for now, just know that arrays are stored one after the other in memory. They're all in the same memory location. We'll come back and take a look at pointers in depth in a future topic. The last thing then, array out of index range. Right. What happens if we go ahead and create an array that's of size 5? We initialize it to some values. We have another variable x that I'm just throwing in here. And now I'm going to use a loop, and I'm going to say in I equals 0, I less or equal to 5. I'm going to increment I by 1. I'm just going to go through and print out the array contents. All right, we can see that our array contents should be 0, 1, 2, 3, and 4. By now, you should have likely spotted my error. Right? Because there are 5 elements, how often will this statement be true? This statement will be true when I is 0, 1, 2, 3, 4, and 5. But do we have an index location 5? No, we do not have an index location 5. And in this example, when I tried to access it, right, when I ran this program, there's no warning from the compiler. And it actually, so you're given some extra memory when your program runs. And this just, all it did was access some area of memory that our program had access to, and we didn't get an error. And these kind of errors are really, these are runtime errors. They're difficult to detect. Usually what happens is if you start getting data that doesn't make logical sense with your array, I mean, you might go back and check your math, or go back and check your processing. but you'll want to always go back and check your array bounds. So that's something the compiler, the system does not tell us when we've gone beyond our memory. And if we actually want to just go ahead and run that right now in here with an example, so int x, let's make this 5, right, and initialize those to 0, 1, 2, 3, and 4, so 5 values. Oh, sorry, I think I made that a. I just made another variable x to throw into memory. It's not really needed. When I was doing this, I wanted to see if perhaps we would overwrite the, excuse me, x's memory. We did not. Used to be years ago you would, but because systems are now giving you extra memory space, you are not overwriting something immediately next to it. Which is probably a decent security feature. All right, so I said here, for int I equals 0, I less than or equal to 5, plus I. And we're just going to print out, right, a at index I. So I'm just using that notation so you can see that. And then we'll refer to this a at index I to read that, and we'll write each one on its own line. And let's do a run to cursor. All right, so you can see in this case when this popped it up, right, if we take a look at memory here, right, we can see 0, 1, 2, 3, 4. We can see x still has 99 in it. But this just reached out to some extra area of memory that was created beyond our array and gave us garbage. And so if we were trying to do math right, with some of this and we were getting some strange values, like I said, go back and look at your memory location. You get a strange printout value. Go back and look at this. You'd say, I should not have a value that looks like that. Probably the first thing I would do is check my array boundaries. Then if my array boundaries are fine, then I know it's probably the logical processing that I'm doing on it, and I would need to check my logic. Like I said, there was no compilation error warning when we built this. If I stop the debugger, if I just go ahead and say, let me clean out, so that just cleans out all the old files. If I just say compile, see, 1 succeeded, 0 failed, got no warnings going on. It lets me do that. Right? So we have to be very careful when we work with our array boundaries, right? We could fix this then if we were to just change that to less than 5, right? We wouldn't access that I at index 5 location. All right, so that's what I wanted to say about arrays, initialization, right? Make sure you don't go out of range with an index. That's an easy, typical thing to do. Don't feel bad if it happens to you. It happens to everyone. All right.